Hello and welcome back. Today we are going to take something that often feels confusing, which is how a linear transform becomes a matrix and make it very clear as to how it works. So we'll start from the basics and build slowly, and by the end we'll have a beautiful example about rotation matrix. So by the end of this video, you'll understand why columns of a matrix are transformed basis vectors and why rows compute coordinates and how the entire idea falls naturally out of linearity. Let's start with a vector space X, and let's assume that it has two basis vectors. So this is a vector space X and it has two basis vectors v1 and v2. Now we know that a vector in this vector space X can be written as a linear combination of these basis vectors. So we could say that there is a vector X in this space which can be written as x1 v1 plus x2 v2. What this tells us is how much of v1 do we take um, here for x1, and x2 tells us how much of the v2 do we take from the basis vectors. So we write the coordinates of x as x1 x2. So this is extremely important that we represent vectors using coordinates relative to these basis vectors. And so what we can now do is look at linear transformation. Imagine we have a linear transformation A. So linear transformation A. If we give it a vector x, so if we give this a vector x, it outputs another vector y. And so today in this video, what we are going to look at is how to write this transformation matrix. So just as we had the basis vectors in X that we looked here, we can also pick basis vectors for Y, which is this output space, right? This one, and let's say those basis vectors are u1, u2, all the way up to um. And we can again write any y vector in this space as combination of these. So y1 u1 plus y2 u2 plus all the way up to ym um. Now with that idea that we have a basis set for this input space, which we are going to say it is going to v1 v2 all the way up to vn, and we have basis set here for the output space y, which after transformation, which is u1 u2 all the way up to um. Now we can write this in a general form. For x we can say that x so x is equal to summation of I is equal to 1, let's say we use j is equal to 1 to n x of j v of j. That's for x, and we can apply the transformation x to x. So we can write that a of x is equal to a, and then inside of parenthesis we have j is equal to 1 to n x of j v j. Now because a is linear, we know that a is linear because we are talking about linear transformation. This a that we have, it can go inside of the parenthesis, and so this could be written as summation j is equal to 1 to n x of j a v vj. And this is very important because Now we know what happens to each basis vector Vj. uh, if we know that, then we know what happens to uh, every vector x when the transformation happens. Now to build a matrix, we can describe each of the a Vj that we have here using the basis of the output space, the UIs. So we could say A1 j U1 plus A2 j U2 plus all the way up to AMJ UM. So those coefficients Aij, A1j, so these coefficients Aij, they are going to become the entries of our matrix. That is our transformation matrix. So what we do now is we substitute that expansion back in the equation above. So here we say A of x is equal to summation j is equal to 1 to n x of j, and within parenthesis again we write summation I is equal to 1 to m aij ui. So that's the summed term that we would write here. So this would not be nothing but sigma I is equal to 1 to m aij, and this would be u of I. That's exactly what we wrote here. So now if we reorder the terms inside in this above equation, what we can get is this is the summation I is equal to 1 to m parenthesis, then summation j is equal to 1 to n aij xj, and then we have u of I right here. Now we try to equate this with the coordinate expression of y. So I'm going to change the colors here again. Let's use this. So y is equal to summation I is equal to 1 to n, 1 to m. I think that's what we have been writing. yi u of I. So we can say a of x is equal to y is equal to, because why is it equal to y, because that's the transformed vector we are talking about. And here we say sigma or summation I is equal to 1 to m yi u of I, and that's what we just wrote above. And since the vectors ui are linearly independent, the coefficients must match, and therefore we can say that yi is equal to summation j is equal to 1 to n a of ij xj. These are the coordinate formulas that define the matrix multiplication. So if we now look at the big picture, what we have is let me write that clearly. This is y1 y2 all the way up to ym, and then we have this A matrix written as a11 a12 all the way to a1n a21 a22 all the way up to a2n, and then down here we have am1, then am2 all the way up to amn, so n, and this is we have the vector x here, which is x1 x2 all the way up to xn, and this is how this is our matrix that we were looking for. This is the A that we have. So point to remember here is that when we multiply a matrix by a vector, we are really combining the transformed basis vectors scaled by the components of our input vector. And so what these rows in the transformation matrix tell us is these. So if we look at these rows, these tell us how each of these weights sort of help, each of these weights work with the values here, coordinates here, to get us the new coordinate in y. And on the other side, if we look at the columns, each column in here, that tells us how this vector that we have will move or point in a specific direction in the new um, output space for that output vector. Now let's look at an example, which is the rotation example. And here we can write the basis as S1. So standard basis S1, let's say S1 is equal to 1 0, S2 is equal to 0 1. Now we rotate, let's say we rotate S1 first. So to rotate S1, we could do the following: a S1 is equal to cos theta sine theta, and this gets us cos theta S1 plus sine theta S2. Likewise, we can rotate S2. So this is rotate S1. Now we rotate S2. So we say a S2 is equal to minus sine theta cos theta is equal to minus sine theta S1 plus cos theta S2. Now to form the matrix using columns, we can write A is equal to cos theta sine theta, that's for the basis vector S1. Then we have minus sine theta cos theta, that is for the basis vector S2. And here we can test on a vector. So let's say our original vector, that let's say this is the space we have. I probably should draw a straight line. Let's get a straight line. So we have one straight line here, another line here, and now let's try and draw an arrow in the space. Let's say our arrow is this, which is 1 1, and we would like to see if or how our transformation matrix A that we just created can help us rotate it 90 degrees to this position right there. So to do that, here is what we are going to do is perform the transformation. So this is 1 1, let's say this is 1, this is again 1, and so this is going to be minus 1. And so what we are saying is this is the 90-degree rotation via this particular matrix that we have. If x is equal to 1 and x is equal to 1 1, and we assume that theta is equal to 90 degrees or pi by 2, then the a that we have becomes 0 1 minus 1 0, and therefore y is equal to this 0 minus 1 1 0, and then we dot that with the x. This is our a, this is the x. So what we get is 0 times 1, so 0 times 1 plus minus 1 times 1, so plus minus 1 times 1, and then we have again 1 times 1 plus 0 times 1, 1 times 1 plus 0 times 1, and so this is 0, this is 0, what we end up with is minus 1, 1. And that is exactly what we have here. This is minus 1, 1. So have rotated the vector that we have here in the blue arrow uh, by 90 degrees to a new position, which is shown here by the red arrow, which is uh, which is pointing at 1 minus 1, 1. And that's it. So now you understand where the matrix comes from, why each column is a transformed basis vector, why rows compute the coordinates of the output, and how to use this to build real world transformations like rotations that we just saw. If you have any questions, comments, or suggestions, please do let me know in the comment section below. I hope to see you all in the next video. Thank you.